Hello, Tensor friends. Yesterday I did a video using the Kronecker Delta, and I keep calling the Kronecker Delta a tensor. Is it a tensor? How do I know it's a tensor? Because Professor Grenfield told me it was a tensor. How do I know it's a tensor? Let's prove that. Okay, the easy answer is this is probably the first time I ran into the Kronecker the Delta was the dot product of a covariant basis vector with a contravariant basis vector is the Kronecker, the delta. Um, now, what does that mean? How do we know that this is a tensor and this, the product of a tensor with a tensor is a tensor? Well, how do we know this is a tensor? Because it follows these rules. So what is the definition of this basis of the vector? It's the derivative of a position vector with respect to a coordinate. And I can rewrite that using the multivariable to chain rule as the derivative of that vector with respect to a prime, the coordinate, and then the derivative of that prime, the coordinate, with respect to the original, the coordinate. So this now becomes this definition, EJ prime, and this has a special name we call the Jacobian, okay? And you just follow where the indexes are. You got an upper and a lower and a lower, so they're all in the right order. And we know this this basis vector transforms covariantly according to this rule. You can prove this in any coordinate system you want. It works. Okay. Now, is the product of a tensor with a tensor, is it always a tensor? I don't presume to know the answer to that. I know all the ones I've worked with are. Here's another example. The dot product of a basis vector with another basis vector gives the metric the tensor, and this is a tensor. You can prove it is using the same rules. Okay, so that's the easy answer. Yes, it is a tensor, but let's do it the way it's supposed to be done. It's more fun. Okay, so if it's a tensor, it's going to transpose according to these rules. So the delta in the prime, the system, will transpose into the unprimed the system using these two Jacobians. Because you have a two-index tensor, you need two of these guys. So this is my free index, I prime. So you got to put it where it's supposed to be in the upper. The other free index is the J prime. You got to put it where it's supposed to be in the lower, and fill in everything else with I's and J's, uppers and lowers, such that they're all the summation indexes, the dummy indexes, right? Okay, so let's let I equal J. So everywhere there's an I, I'm going to replace it with a J. And I get this. So here, if I equal J, we got JJ, and that's just 1. Else it's going to be 0, so we got 0 equals 0, and that's really not much fun. All right, so I replace this I with a J. Now look at this. So this is what we actually did in the video right before this. This is a contraction. So this J gets absorbed, and we're left with this J I prime J prime equal, or does it equal the Kronecker delta I prime J prime? Well, what actually is that? This mean? Well, once again, if we leave them unequal, we got 0 equals 0, and that's boring. So let's let I prime equal J prime. Well, now we got this, J prime, J prime, J prime, J prime. What's that? Well, that's the partial of x J prime with respect to itself. And we know that's 1. So, yes, that means that this transforms the way it's supposed to in any coordinate the system. I prime, J prime, if they're equal, it's going to be 1. If they're not equal, it's going to be 0. So that's it. Wasn't that fun? I'll see you later.